Pluto drives them to climb and plunge as its orbit crosses the path of another planet at the furthest reaches of our neighborhood planetary framework. Pluto, the baffling little planet, is producing a ton of energy in the field of space science. Ongoing advancements suggest that Pluto might actually crash into Neptune, causing anxiety among astronomers and space aficionados. Notable figures like Neil deGrasse Tyson and Michio Kaku have raised alarms about the possible outcomes of this celestial event. Yet, how did Pluto end up on a collision course with its neighboring planet? Besides, what could this infinite conflict suggest for life on Earth? Join us as we explore how Pluto's orbit is converging with Neptune and why this phenomenon is leaving researchers concerned. Once considered a distinct planet, Pluto underwent a reclassification and is now referred to as a dwarf planet due to its irregular orbit. Despite this downgrade, Pluto continues to captivate and intrigue the astronomical community. Recently, concerns have been raised by respected scientists, such as Neil deGrasse Tyson and Michio Kaku, regarding Pluto's path, which may bring it into closer proximity to Neptune. This alignment suggests a series of potential interactions between these two celestial bodies, with significant implications for Earth. Pluto's orbit around the Sun is remarkable, distinguishing it within our solar system. Its orbit is highly elongated, covering vast distances as it travels. Since its discovery in 1930, Pluto has yet to complete a full revolution around the Sun, adding to its mystery. Unlike the more circular orbits of the major planets, Pluto's orbit is unusually stretched, making it a distinctive feature in our solar system. The tilt of Pluto's orbit is another fascinating aspect. Deviating 17 degrees from the ecliptic plane, it has a sharper angle compared to the orbits of other planets. This combination of its eccentric and elongated orbit adds layers of complexity to Pluto's movement around the Sun. One particularly intriguing characteristic is its periodic association with Neptune's orbit. For nearly 20 years in each cycle, Pluto's orbit brings it closer to the Sun than Neptune's, defying expectations given their respective positions. Notably, Pluto's orbit is not circular but elliptical, leading to significant fluctuations in its distance from the Sun. At its closest approach, Pluto reaches about 30 astronomical units, AU, from the Sun, while at its farthest, it extends beyond 49 Australian dollars, twice Neptune's distance from the Sun. Moreover, Pluto's orbit is tilted at a crucial angle relative to the major planets, contributing to the complexity of its trajectory and interactions with other celestial bodies, especially Neptune. When Pluto and Neptune do align in their orbits, their gravitational forces alter their trajectories over time. This intricate relationship highlights the interconnectedness of celestial bodies, with each object exerting gravitational influence over the others, shaping their orbits. In recent years, advancements in observational technology have enabled astronomers to track Pluto's path with remarkable precision, providing deeper insights into its orbit and its potential impact on the stability of the outer solar system. While a direct collision between Pluto and Neptune remains unlikely, the possibility cannot be entirely dismissed, prompting increased interest and research from the astronomical community. Despite its small size and distant location, Pluto continues to command attention. So why hasn't a collision occurred between Pluto and Neptune? The answer lies in the gravitational interactions between planets. When astronomers began studying Pluto's orbit, they were puzzled by its unusual behavior. Unlike most planets, which maintain a stable plane as they orbit the Sun, the ecliptic plane, Pluto's path deviates sharply, adding an extra layer of mystery. The real puzzle emerged when scientists realized that Pluto's orbit intersects Neptune's path. Yet, despite this unusual overlap, Pluto's orbit remains stable, which speaks to the intricate mechanics of space. Understanding how celestial bodies like Pluto, Neptune, and the Sun interact gravitationally is a significant challenge for astronomers. Predicting the movement of these bodies is similar to calculating their future positions based on their initial conditions and the forces they exert on one another. For Pluto, the interaction between its orbit, Neptune's orbit, and the Sun's gravitational pull creates a delicate and coordinated system that allows Pluto's path to remain predictable. Terms such as precession, libration, and the VSOP variations help scientists navigate these complex dynamics. Understanding these principles is essential for maintaining the stability of planetary orbits. When Pluto crosses Neptune's path, it is still about 90 degrees away, preventing a direct impact. The phenomenon of libration ensures that Pluto remains safely out of Neptune's way, even when it approaches. The VSOP variations, named after researchers von Zeipel, Pacer, and others, explain why Pluto's orbit may seem erratic yet remains predictable over time. Despite the apparent chaos of space, specific patterns and rules help keep objects in orbit. These principles work to stabilize Pluto's orbit, mitigating the risk of a collision with Neptune. The potential for orbital instability highlights how sensitive a celestial body's orbit is to its initial conditions. Even small changes in a planet's position or velocity can lead to significant shifts in its trajectory over time. Using complex computational simulations, astronomers can model Pluto's movement in space, observing how slight changes in variables can drastically alter its orbit. In the late 20th century, these simulations revealed that Pluto's orbit, while seemingly stable, can be subject to chaotic fluctuations. Even minor differences in Pluto's initial position or speed can lead to significant changes over long periods. Nevertheless, Pluto's orbit has remained relatively stable for billions of years, suggesting that despite its apparent instability, its movement follows a discernible pattern. However, predicting the behavior of planets with such irregular orbits is a challenging task. These systems are so unpredictable that long-term forecasting becomes difficult. Simulations are useful in estimating potential outcomes, but they also demonstrate the inherent unpredictability of these celestial movements. Gaining a better understanding of Pluto's orbit is crucial, especially when examining whether a collision with Neptune could occur in the future. This knowledge helps us understand how our solar system functions and reminds us that even seemingly unstable orbits can be stabilized by gravity and broader cosmic dynamics. Exploring space reveals many surprises, and Pluto's orbit is a perfect example of such phenomena. Unlike the orbits of other planets, Pluto's path around the Sun is more elliptical, meaning it is not a perfect circle. At times, Pluto even ventures closer to the Sun than Neptune. This creates interesting dynamics, especially since Neptune is also moving along its own path. While the probability of Pluto and Neptune colliding remains low, it is essential to recognize the forces at play. Gravitational force acts as an invisible hand, keeping the planets in their orbits. So, although Pluto and Neptune may seem to be on a collision course, their paths are meticulously shaped by gravity. Studying Pluto's orbit provides valuable insights into the delicate balance of forces. Tyson finds the mysteries of space fascinating and believes that events like Pluto's reclassification help engage the public in the pursuit of space science. He works alongside other experts to raise awareness about the potential risks of Pluto's orbit, particularly its possible collision with Neptune. Tyson suggests that such an impact would be a monumental event for the entire solar system, with consequences that could ripple across the universe. A collision between Pluto and Neptune would release enormous amounts of energy, potentially causing Pluto to break apart, sending fragments hurtling through space. These debris pieces could collide with other celestial bodies, further disrupting the solar system's delicate balance. Even Neptune would not be unaffected. Its orbit could be altered significantly due to the impact, potentially affecting its gravitational influence on nearby objects, including its moons. Michio Kaku, a well-known theoretical physicist, shares similar concerns. He has emphasized the importance of monitoring Pluto's orbit, given its unusual trajectory and interactions with Neptune's gravitational field. Kaku warns that while a direct collision is unlikely in the short term, long-term gravitational perturbations could shift Pluto's path, increasing the chances of an impact over millions of years. Both Tyson and Kaku stress that understanding Pluto's orbit is essential not only for predicting potential collisions, but also for gaining deeper insight into the mechanics of celestial interactions. The study of Pluto and Neptune's orbital dynamics offers valuable lessons about how gravitational forces shape the evolution of planetary systems. The role of orbital resonance. One of the key reasons a direct collision between Pluto and Neptune has been avoided is due to a phenomenon known as orbital resonance. Pluto and Neptune are locked in a 3:2 resonance, meaning that for every 3 orbits Pluto completes around the Sun, Neptune completes 2. This gravitational relationship ensures that the two planets never come too close to each other, maintaining a stable configuration over long periods. Orbital resonance acts as a cosmic safeguard, preventing disruptive encounters between celestial bodies. Similar resonances exist throughout the solar system, helping maintain order and stability despite the complex gravitational interactions at play. However, while resonance protects Pluto and Neptune from a direct collision for now, it does not mean their orbits will remain unchanged indefinitely. Over extremely long timescales, gravitational interactions with other planets, particularly Jupiter and Saturn, could cause subtle variations in their orbits, potentially altering their resonance and increasing the risk of close encounters in the distant future. The future of Pluto's orbit. Astronomers continue to use advanced simulations and telescopic observations to refine their understanding of Pluto's orbit. While current models suggest that a catastrophic collision is highly unlikely for millions, if not billions of years, uncertainties remain. The chaotic nature of celestial mechanics means that even small perturbations can have significant long-term effects. New discoveries about Pluto's internal composition, atmosphere, and interactions with the Kuiper Belt also contribute to our understanding of its future. As space missions like the New Horizons probe continue to provide valuable data, scientists are gaining a clearer picture of Pluto's behavior and how it fits into the broader framework of our solar system. Conclusion. Pluto's orbit is a fascinating case study in celestial mechanics, illustrating the intricate dance of gravitational forces that shape planetary motion. While the possibility of a collision with Neptune is low, it remains an important topic of research, highlighting the unpredictable nature of space. Through ongoing observations and advancements in computational modeling, astronomers strive to unlock the secrets of Pluto's journey through the cosmos. Whether as a planet or a dwarf planet, Pluto continues to inspire curiosity and debate, reminding us of the ever-evolving nature of scientific discovery. In the end, Pluto's fate remains intertwined with the gravitational ballet of our solar system. By studying its orbit and interactions with Neptune, scientists gain deeper insights into the forces governing the universe, offering a glimpse into the cosmic clockwork that keeps our solar system in motion. Physicist Michio Kaku offers his own point of view on the relationship between heavenly mechanics and space exploration. Kaku stresses that studying Pluto's orbit can provide crucial insights into the future of space exploration. He believes that understanding the complex gravitational interactions between celestial bodies like Pluto can improve future missions, helping us navigate the solar system more safely and predict potential risks. Kaku's work in theoretical physics, especially in string theory, aims to decipher the fundamental laws governing the universe. He proposes that by studying the dynamics of celestial bodies like Pluto, we can unlock deeper understanding of the forces that shape our existence. Both Neil deGrasse Tyson and Kaku agree that observing events, such as a potential Pluto-Neptune impact, presents an exciting opportunity to learn more about the universe. In particular, such an event could have significant implications for our understanding of string theory. String theory seeks to explain the fundamental forces of nature by modeling the universe as a series of one-dimensional strings. A Pluto-Neptune collision could create extreme conditions that would provide valuable data for testing string theory's predictions about space-time. While the immediate impact on Earth would be negligible due to our distance from the outer solar system, the scientific knowledge gained from such an event could be groundbreaking. It would expand our understanding of the fundamental nature of the universe, pushing the boundaries of theoretical physics and astronomy. As researchers continue to study the gravitational effects of neighboring planets like Neptune, the dynamic and ever-changing nature of space becomes increasingly clear. However, space remains full of mysteries. The three-body problem, where multiple celestial bodies exert gravitational influences on one another, is just one of many complexities that scientists are working to solve. The ongoing exploration of space is essential for expanding our knowledge of the universe and the principles that govern it. Although the probability of planetary collisions is very low, the possibility still exists due to the influence of gravitational forces. These forces can alter planetary orbits, potentially leading to collisions over time. One example of this phenomenon is the TRAPPIST-1 system, which contains 7 Earth-sized planets. The gravitational forces between these planets can create orbital resonances, making their orbits less stable and possibly leading to collisions in the future. Scientists are closely monitoring these systems to better understand how celestial bodies interact and how planetary paths can shift. In addition to planetary interactions, rogue planets, planets that no longer orbit a star, can drift through space. These planets, once part of a star system, can travel vast distances and occasionally collide with other star systems. However, the immense emptiness of space means that the chances of a rogue planet colliding with another planet are low. Despite their rarity, rogue planets are fascinating objects of study for astronomers. Finally, when galaxies collide, the gravitational forces involved can alter the formation of stars and planets. While planets may not collide directly, their orbits can be disrupted, potentially ejecting them into space or causing them to collide with other planets or their host stars. This disturbance can lead to the formation of new celestial bodies or even the birth of new stars. The late heavy bombardment theory suggests that around 4 billion years ago, an increase in impacts from comets and asteroids occurred, likely caused by the migration of outer planets like Jupiter and Saturn. These impacts disrupted the orbits of smaller objects in space, many of which were ejected into the inner solar system. While these impacts did not involve direct planetary collisions, they serve as a reminder of gravity's power to reshape the trajectories of objects in space. The late heavy bombardment hypothesis is a fascinating concept that suggests the early solar system experienced intense cosmic bombardment. During this period, the outer planets, such as Jupiter and Saturn, are believed to have undergone significant migrations, displacing many smaller objects and sending them on erratic trajectories. As a result, these objects crashed into the inner planets, leading to significant impacts. While these encounters did not involve direct planetary collisions, they influenced the surfaces and compositions of planets, especially Earth. Some scientists even believe that this bombardment may have played a role in delivering essential elements, such as water and organic molecules, to our planet, contributing to the conditions necessary for life. These impacts, which occurred billions of years ago, serve as a stark reminder of how gravitational forces from larger bodies can disrupt the movement of smaller celestial objects, altering their orbits and trajectories. In this case, the powerful gravitational effects of Jupiter and Saturn were instrumental in shaping the paths of many objects that eventually found their way into the inner part of the solar system, further complicating the delicate balance of forces at play in our cosmic neighborhood. The effects of these early cosmic collisions can still be seen today in the craters found on the surfaces of planets, moons, and asteroids. Such events highlight the complexity of space and the fragility of planetary orbits. Similarly, Pluto's eccentric orbit raises concerns about the possibility of a future encounter with Neptune. The larger historical impacts of cosmic forces help scientists understand how planetary systems evolve over time. The idea that celestial bodies can collide or influence each other's trajectories serves as a reminder of the dynamic nature of space and the potential consequences these interactions may have on life within our solar system and beyond. The delicate interplay of gravitational forces is further exemplified by the concept of the three-body problem, an age-old challenge in physics and astronomy that describes the difficulty of predicting the motion of three celestial bodies that gravitationally influence each other. As we observe the interactions between planets like Pluto, Neptune, and others in our solar system, we are reminded of how challenging it is to predict long-term orbital paths with certainty. Despite advances in computational simulations and observational technology, the exact movements of these bodies remain elusive, especially considering how even tiny variations in velocity or position can have significant effects over long periods. Furthermore, experts remain vigilant about the potential risks posed by rogue planets, celestial bodies that no longer orbit a star and instead drift through interstellar space. These planets, ejected from their original solar systems due to gravitational disturbances or close encounters with other stars, present a unique challenge to our understanding of planetary dynamics. While they are rare, their presence in the universe highlights the unpredictable nature of space. Over time, rogue planets can travel immense distances, occasionally approaching other star systems. However, the vast emptiness of space makes direct collisions with other planets or stars highly unlikely.